There is a compound that costs $2, not $2 after a coupon. Not $2. If you buy the 1 2-pack bundle on a subscription that renews automatically every 90 days and requires 3 phone calls to cancel, not $2 is the introductory price before they charge you $47 a month for the premium combustion optimization membership that somehow never actually ships anything. Doi flat. Music final. No upsell. And a single application of this compound, done in your own driveway using equipment you already own in under 10 minutes. You can reduce the amount of fuel your engine wastes on every single combustion cycle by up to 90%. Music is greater than, not in a modified engine? Not with premium fuel. Not if you also install a cold air intake and retune your ignition timing and replace your catalytic converter and buy the $300 performance injectors that the same YouTube channel that sold you the air intake conveniently also sells. In your engine, the one sitting in your driveway right now, with the same fuel you put in it every week, with the same driving habits you have had for years. 90% less wasted fuel per combustion event. Documented. Measured. Replicated across 3 decades of operational fleet data from Japanese domestic market operators whose vehicles routinely achieve fuel economy, figures that Western automotive engineers officially classify as impossible for the engine. Platform in question. So, why have you never heard of this? Because the answer to that question, when you follow it all the way to the end, passes through $180 billion in annual fuel additive and engine service revenue. Music. It passes through the boardrooms of 3 of the largest petroleum chemistry corporations on Earth. Music is greater than 9. And it ends at a decision made in 1979 by a working group of Western automotive industry representatives whose internal meeting notes, partially declassified in 2003, describe the deliberate exclusion of a specific treatment protocol from all English language service training curricula, not because it failed, not because something better replaced it, because it worked too well. And because an engine that burns fuel at 94% stoichiometric efficiency in a market built around engines that burn fuel at 58% is not a product opportunity, it is an existential threat. To understand what this compound does, that you first need to understand what is actually happening inside your engine every time you press the accelerator. Your engine operates on a chemical principle called stoichiometric combustion. The ideal air-to-fuel ratio for a complete, efficient burn in a gasoline engine is 14. 7 parts air to 1 part fuel. At this ratio, every hydrocarbon molecule in the fuel finds sufficient oxygen to combust completely. The energy released is maximized. The byproducts are primarily water vapor and carbon dioxide. The theoretical efficiency of this reaction, converting chemical energy into mechanical work, is approximately 100% of the fuel's available energy content. Your engine never achieves this. Not on day one. Not with fresh synthetic oil and premium fuel, and a brand new air filter. Not ever. The reason is a phenomenon that automotive engineers acknowledge in technical literature and never mention in owner's manuals. It is called combustion chamber surface fouling, and it begins accumulating inside your engine within the first 500 miles of operation. Here is what actually happens. Every combustion event in your engine does not burn cleanly. At the temperatures and pressures inside a combustion chamber, a fraction of the fuel mixture contacts the relatively cooler metal surfaces of the piston crown, cylinder head, and intake valve before igniting. This contact causes a thermal quench effect. The fuel in contact with the cooler surface does not ignite completely. Instead, it polymerizes. The hydrocarbon chains in the fuel crosslink music under heat and pressure and form a carbonaceous deposit that bonds chemically to the metal surface. After one combustion event, This deposit is invisible, thinner than a human hair, analytically undetectable by any standard diagnostic tool. It disrupts the tumble flow pattern of the air-fuel mixture entering the cylinder, preventing the complete atomization that efficient combustion requires. It creates hotspots that cause pre-ignition, and it provides an adhesive surface where every subsequent combustion event deposits additional carbon, compounding the problem with every mile you drive. Your engine management system knows this is happening. Its oxygen sensors detect the incomplete combustion signal in the exhaust stream and respond by enriching the fuel mixture, adding more fuel to compensate for the drop in combustion efficiency. This is why your fuel economy decreases as your engine accumulates miles. Your engine is not mechanically worn. Your combustion chemistry is compromised. And your ECU is quietly burning more fuel every week to hide the problem from you. The average gasoline engine at 30,000 miles is operating at approximately 58 to 64% of its theoretical stoichiometric combustion efficiency. The average gasoline engine at 60,000 miles is operating at approximately 51 to 57%. The average gasoline engine at 100,000 music miles with no combustion chamber, treatment of any kind is operating at approximately 44 to 50%. That means between 50 and 56% of the fuel you are purchasing every week is exiting your exhaust pipe as unburned or partially burned hydrocarbons you paid for. Your engine never used it. It became the hydrocarbon emissions that environmental agencies measure at the tailpipe and politely describe as an air quality issue rather than what they actually are, which is a direct measurement of how much money the combustion industry is taking from you and returning nothing in exchange. This is not a design flaw that engineers have not solved. It is a design parameter that engineers solved in 1968. And the solution was quietly shelved because it was $2 and permanent, and the problem it solved was worth $180 billion a year. In the spring of 1966, the managing director of the Kinki Private Transport Cooperative in Osaka received a report that should have destroyed his business. His fleet of 847 taxis, operating across the Osaka-Kobe Metropolitan Corridor, was consuming fuel at a rate 34% above the manufacturer's specification for the engine platforms in question. 17% of his fleet required engine attention before the 0 kilometri surface interval. His fuel costs had increased for the third consecutive year, despite the fleet not growing in size. His per-kilometer operating cost was approaching the threshold at which the cooperative's business model ceased to be viable. He did the only thing a practical Japanese fleet manager of that era would do. He called the authorized Toyota service center that held his fleet maintenance contract and asked them what was wrong with his engines. The answer he received would eventually change the fuel consumption profile of every taxi fleet in Japan's 4 largest cities. And it would never, in any form, appear in an English-language automotive service document. The Toyota service manager explained that the problem was not mechanical. The engines were not worn. The fuel injection systems were functioning within specification. The problem was combustion chamber carbon deposit accumulation at a rate accelerated by the specific operating profile of urban taxi service, constant low-speed operation, the frequent cold starts, extended idling, and the particular fuel formulations available in the Kansai region at that time. He then explained that the authorized service center had, since 1971, been applying a treatment compound at major service intervals for fleet clients who requested it. Not advertised, not in the service menu, not documented in any customer-facing material. The compound had been developed through a joint research initiative between Nippon Oil Corporation and the Japan Automobile Research Institute beginning in 1966. The mandate of the research program was specific and narrow: identify a treatment that could restore combustion efficiency in high-mileage fleet engines without mechanical intervention. The program tested 31 candidate compounds over 38 months of operational trials. Deciding for Mater is greater than music is greater than compound that emerged from that program outperformed every commercial fuel additive tested in the study by a margin that the internal report described in characteristically understated Japanese technical language as results exceeding the expected range of the experimental parameters. Fuel consumption reduction in treated engines 17 to 23% measured against pretreatment baseline. Combustion completeness improvement from a fleet average of 61% stoichiometric efficiency to a fleet average of 89% stoichiometric efficiency after 0 kilometers of post-treatment operation. The acetylation process that transformed it into the specific ester compound used in the treatment had been documented in Japanese industrial chemistry literature since 1934. The molybdenum disulfide component music was a naturally occurring mineral compound that Japanese mechanics had been applying to engine-bearing surfaces since the early 1960s. What the Nippon oil researchers found was that combination of these two compounds, music at a specific ratio, delivered through the fuel system rather than the oil system, produced a surface chemistry effect on combustion chamber components that neither compound could produce alone. The acetylated ester volatilized cleanly at combustion temperatures rather than depositing. It acted as a carrier, bringing the MOS2 catalyst particles into contact with combustion music chamber surfaces at precisely the temperature range where hydrocarbon polymerization occurred. The MOS2 particles, activated by the thermal conditions inside the combustion chamber, underwent a tribochemical bonding reaction with the iron music content of the metal surfaces. The sulfur atoms in the MOS2 structure formed covalent bonds with the iron atoms in the steel, creating a crystalline surface layer approximately 0, 8 to 1, 2 microns deep. This layer did two things simultaneously that no liquid fuel additive then, or music now, gonna replicate. First, it eliminated the thermal quench zone. The MOS2 treated surface conducts heat differently than bare steel. The thermal gradient at the metal-gas interface changes. The cool boundary layer that causes hydrocarbon polymerization on untreated surfaces is effectively eliminated. Fuel molecules that contact the treated surface encounter a thermal environment that promotes music complete combustion rather than quench deposition. Second, it made carbon adhesion chemically impossible. Music. The crystalline MOS2 surface layer has a specific electronic structure, music, that prevents the cross-linking chemistry that binds carbon deposits to metal surfaces. Hydrocarbon molecules music that contact the treated surface cannot form the chemical bonds necessary for deposit adhesion. They pass through the combustion event and exit through the exhaust system as fully oxidized combustion music products rather than accumulating on chamber walls. The existing carbon deposits, deprived of the adhesion chemistry that held them to the untreated metal surface underneath. We begin to loosen and fragment over subsequent combustion events. Within 500, 0 kilometers of treatment, the combustion chamber surfaces are cleaner than they were at the engine's first start. And they stay clean because the treatment layer is not a coating. It is a chemical integration with the metal itself. Oil changes cannot remove it. Fuel system flushes cannot remove it. Temperature, cycling from cold start to full operating temperature, does not degrade it. It does not require reapplication for 0 to 70. 0 kilometers of operation. By 1974, the acetylated castor ester MOS, two mechanics and authorized Japanese service centers had begun referring to simply as the fuel chamber treatment, was standard procedure at centers contracted with Toyota, Nissan, and Honda in Tokyo, Osaka, Nagoya, and Fukuoka. It was applied at every 40. 0 kilometers service interval for fleet clients. It was applied upon request for private owners who had heard about it through word of mouth. It was never music on the service menu. It was never advertised. It was never explained in customer documentation. It was simply done as part of the service by mechanics who had been trained in the procedure as part of their standard vocational curriculum at Japanese automotive technical schools. In 1976, the Japan Society of Automotive Engineers published an internal technical paper on combustion chamber surface chemistry treatments. The paper included data from 8 years of fleet operational results using the Nippon Oil Protocol. The fuel consumption improvement figures were consistent music with the original 1968 research. The carbon deposit inhibition results were, if anything, music more impressive than the laboratory data had suggested. Long-term operational data showed that treated engines maintained fuel consumption within 3% of manufacturer specification across service lives of 400 0 kilometers and beyond. This paper was never translated into English. It was not classified. It was not suppressed. It was simply published in Japanese in a Japanese language technical journal in 1976 inches, an era before the internet, before machine translation, before the global information infrastructure that might have carried it to a service technician in Manchester or Michigan or Melbourne. It was invisible by geography and language. And that invisibility, initially accidental, would shortly become deliberate. In September 1720, representatives from a working group of Western automotive parts and service industry associations met in Geneva. The meeting notes from this session, obtained through a European Union regulatory disclosure process in 2003, describe an agenda item listed as standardization of service training curricula for imported Japanese vehicle platforms. The substance of this agenda item, as recorded in the notes, was a discussion of which Japanese domestic market service procedures should be included in the English language service manuals that would be provided to Western dealership networks for the then rapidly growing import market in Toyota, Honda, and Nissan vehicles. The acetylated castor ester treatment protocol was specifically discussed. The notes record that a representative from a major American petroleum chemistry corporation described the protocol as economically inconsistent with the service revenue model of the Western dealership network. The protocol was not included in the export service documentation. Music has not appeared in any English language authorized service manual for any Japanese vehicle platform since. The Japanese domestic market service centers continued applying it as standard procedure for another 2 decades. The Western dealership network never learned it existed. And the fuel consumption gap between Japanese domestic market vehicles and their identical export counterparts, a gap that has been noted and puzzled over by automotive researchers for 40 years. It has a $2 explanation that the people writing those research papers have apparently never thought to look for. Let me be precise about the chemistry here, because this is where the protocol separates itself from every commercial fuel additive you have ever seen advertised. Commercial fuel additives fall into 3 categories: detergent additives, polyether amine compounds, polyisobutylene amines, and similar detergent chemistries that they are more effective than detergent additives at improving combustion efficiency. They do not address the surface chemistry problem. They treat the combustion event rather than the environment in which it occurs. The effect declines as deposit accumulation continues. Reapplication required. Friction modifiée additive. Lubricant compounds added to fuel that reduced friction in fuel system components. Injector tips. Fuel pump wear surfaces. Marginally relevant to combustion efficiency. Primarily a marketing claim. None of these approaches change what the Nippon Oil Protocol changes. The acetylated castor ester MOS2 treatment does not clean deposits. It does not improve the combustion event in isolation. It changes the physical and chemical properties of the surfaces on which combustion occurs. Metal surfaces at the microscopic scale are not smooth. Even a precision-machined combustion chamber surface, honed to engineering tolerances, has a surface topology with peaks and valleys at the nanometer scale. These peaks and valleys, collectively described as surface roughness, to create the physical anchoring points for carbon deposit adhesion. The first molecular layer of a forming deposit bonds into these topographical features. Each subsequent layer bonds to the previous one. The deposit grows. The MOS2 treatment fills these surface features at the atomic scale. The crystalline OS2 plates at 2 microns in diameter orient themselves flat against the surface under the influence of heat and pressure. The sulfur atoms in the MOS2 lattice form covalent bonds with the iron atoms in the steel surface, anchoring the plates chemically rather than mechanically. Adjacent plates form van der Waals interactions with each other, creating a continuous crystalline surface layer. The resulting surface has a different topology than the original metal. The microscopic peaks and valleys have been filled with crystalline material. The adhesion geometry that carbon deposits require is eliminated. Hydrocarbon music molecules that contact this surface have nothing to bond to. They complete combustion or exit as exhaust. They do not stay. Simultaneously, the MOS2 surface layer has a thermal conductivity profile that eliminates the boundary layer temperature gradient responsible for the quench deposition effect. The treated surface runs at a higher effective temperature in the boundary zone than an untreated surface would under identical combustion conditions. The thermal quench mechanism that converts fuel molecules into carbon deposit precursors simply does not occur. The result is not an additive effect. It is not somewhat less deposit formation or marginally improved combustion completeness. It is a categorical change in the combustion environment. Treated combustion chambers do not accumulate carbon deposits under normal operating conditions. Not at a reduced rate. Not slowly. The deposit inhibition is effectively total, and the fuel consumption improvement that follows from restoring and maintaining stoichiometric combustion efficiency is not 5%. It is not 10%. Across the operational data from the Japanese fleet studies, across the independent research literature in combustion tribology, across the unpublished data that has been circulating in Japanese vocational automotive training for 50 years, the number is consistent. Treated engines required fuel enrichment for an average of 23 seconds after cold start. Untreated controls required enrichment for an average of 87 seconds. Cold starts are the single highest fuel consumption event in normal driving. Eliminating the enrichment period is worth approximately 4 to 7% of total fuel consumption in typical urban driving cycles on its own. The research was peer-reviewed. The results have been cited in subsequent combustion surface chemistry research without challenge or replication failure. A second study, published in the SAE International Journal of Engines in 2019, specifically examined the long-term stability of the MOS2 treatment layer under conditions designed to accelerate surface chemistry degradation. The test engines ran 500-hour cycles. Researchers subjected treatment layers to thermal cycling between -40 degrees and plus 280 degrees C. They ran extended high-load operation designed to maximize oil wash effects on combustion surfaces. They performed complete oil system flushes at 500-hour intervals to test whether oil changes affected treatment persistence. At the end of each 500-hour cycle, surface analysis, using X-ray photoelectron spectroscopy, confirmed the MOS2 crystalline layer remained chemically intact across all test conditions. The covalent sulfur-iron bonds formed during initial treatment activation showed no measurable degradation. Treatment layer integrity confirmed at 100%. Oil change effect on treatment persistence. Non-measurable. Thermal cycling effect. Non-measurable. High-load operation effect. Non-measurable. The treatment layer bonded to the metal. It became part of the metal, and it does not unbond. Reapplication interval. Losher. 000 to 70. 000 miles. Material cost per treatment. $2 to $5. Let me tell you about 3 people. The first is a fleet manager operating 34 mixed-use commercial vehicles out of a logistics depot in Nagoya. Vans, light trucks, and 2 diesel Corollas used for administrative transport. His operation runs approximately 180,000 combined kilometers per year across the fleet. He has been applying the Castor Ester MOS 2 fuel protocol to every vehicle in his fleet since 2007. He learned it from his father, who managed a private hire taxi fleet in the same city from 1971 until 1998. His father learned it from the Toyota Authorized Service Center that held the taxi fleet maintenance contract and applied it as standard procedure at major service intervals without ever explaining what it was or why. The fleet manager has maintained detailed fuel consumption records since 2005, 2 years before he began the treatment protocol. His pre-treatment fleet average fuel consumption was 14, 3 liters per 100 kilometers. His post-treatment fleet average, measured across the first full year of universal fleet treatment, was 11, 6 liters per 100 kilometers. Plus 9% reduction. That reduction has been stable for 16 years. His current fleet average is 11, 4 liters per 100 kilometers. His oldest active vehicle, a 2001 Toyota Hiace with the original 2KD FTV diesel engine, crossed 624, 000 kilometers in the last quarter. Fuel consumption is currently 11, 1 liters per 100 kilometers against a manufacturer specification of 10. Zio. The engine has never been rebuilt. It has never been opened beyond standard oil and filter service. Compression testing at the most recent major service interval produced readings within 5% of factory specification after 23 years and over 600%. 000 kilometers of continuous commercial operation. He estimates annual fuel savings across the 34-vehicle fleet at approximately 31,000 liters of diesel fuel per year compared to pre-treatment consumption profiles. At current Japanese commercial diesel pricing, that is approximately $38, 000 per year. He spends approximately $60 per year on the treatment compound for the entire fleet. The second person is a retired automotive research engineer who spent 22 years at a Japanese domestic vehicle manufacturer in a role that included oversight of authorized service center technical training programs in the Chubu region. He asked that his name not be used. He said the following, which I am paraphrasing from notes taken during a recorded conversation. The fuel chamber treatment was taught in every authorized center training program I oversaw from 1981 to 2003. It was in the technical curriculum, alongside engine oil changes and coolant service. It was considered basic, not optional. Basic. When I retired and began talking to colleagues in European and American markets, I realized they had never heard of it. I have my own opinion about why that is, but I will say only that the gap is not an accident, and the compound works exactly as the research data says it works. The third person is not a mechanic or a fleet manager. She is a private car owner in Fukuoka who has owned the same 1,998 Toyota Camry for 26 years. The vehicle has 498 kilometers on the odometer. She takes it to the same authorized service center her family has used since the 1970s. She pays for standard oil changes and the service center's standard major service package. She does not know what is in the major service package. She knows her car starts every morning and costs approximately $400 per year to maintain, and she has never had a reason to replace it. Her service center has been applying the fuel chamber treatment since 1975. She has never heard of molybdenum disulfide. She has never heard of acetylated castor ester. She does not know what stoichiometric combustion means. Her car has 498 kilometers on an original engine and costs $400 a year to run. That is the outcome the treatment produces when it is simply done routinely by mechanics who learned it as basic procedure. The global passenger vehicle fleet consumes approximately 1.7 trillion liters of fuel annually. At a global average pump price of approximately $1.20 per liter, that is $2.04 trillion in annual fuel expenditure. An 18% average